All right, on to part two. Similar example. A cylinder has a radius of 8 meters. There's a given. Water is leaking out at a rate of 2 meters cubed per minute. That's a given. Leaking out. Leaking out. That probably means it's negative, right? What's negative? Well, the volume is changing at a rate of uh, 2 meters cubed per minute. That's dV by dt, right, with respect to time, minute time, is equal to -2, right? How fast is the depth decreasing when the water is 5 meters deep in the tank? Phew, that's a lot of information. Let's write down the required. So we want to find how fast is the depth decreasing. How fast is the depth? That's a derivative, right? It's a rate. The depth. Well, let's get a diagram here. And if we got a tank, something like this. We got a bunch of water in here, like this, like that. When there's 5 meters in the tank, the water's leaking out here. The question is how fast is the depth decreasing? So this is, I guess it's kind of the height of the water. So I'm going to call this then dH dt, and I want that value, that rate, when the water is 5 meters deep. So what's that? Is that the radius? No, that's when the height is 5, right? When the height is 5, we want to find dH dt. Okay, dandy. Well, what's the formula that will relate these things? Well, probably we could write down the volume of a cylinder formula, right? Pi r squared h. And notice if I were to take the derivative right now, it looks like it's going to be a product rule. But, this r is fixed. The radius is fixed here, right? The radius is always 8. Always 8. So I can actually just substitute in for r equals 8. And then I don't have to worry about it being a product rule. Right? It's fixed. It's never changing. So I get volume is 64 pi h, and then that's going to be an easy derivative to take, right? Because now dV by dt and the dH when h equals 5, then I'm off to the races here. So what's the derivative? I've got dV by dt, derivative of this side, and this part's just number, so it's going to be 64 pi, but remember, h is a function of time, so then it's not like I can just leave it alone, then I got to take the derivative of the h, which makes sense because that's what actually I wanted to find. And then I know that dv dt is -2, right? 64 pi is here. And then this is easy compared to those awful optimization questions we had the last few days. This seems to be simple. -1 over 32 pi, which is about what was that in decimal? -0.01 meters per minute. Sounds like somebody's at the door. I don't know if you can hear the dog barking. He's a bad dog. All right, I guess whatever crisis the dog was into has been averted, and now I can finish this question. So when, well, you know what's funny here? I'll just write the conclusion. The height was decreasing at 0.01 meters, 1 centimeter, 10 centimeters per minute. When did we use the height as 5? Well, we didn't. We didn't. So what does that mean? That means for the entire time, the height was increasing by a constant amount. Now, you know from physics or science or whatever that there's a pressure involved that as a tank empties, it actually empties slower and slower with less water in it. So this function probably isn't very accurate, that it should have been some other model, but we're not too worried about that. Um, when there's no place to put in that the value that's given, and it's not that you've made an error, it's just that you might not have needed it. It might have been constant, and that happens from time to time. Okay, last example. This is a fun one. A water tankette is in the shape of an inverted cone um, with a radius of 2 meters and a height of 4 meters. Water is being pumped in, positive volume, right? Positive volume change. Find the rate at which the water level is rising. Water level is rising. Find the rate at which the water level is rising. There's our required when the water is 3 meters deep. So what have I got? My given is, I'm going to draw a picture and draw some of this stuff on a picture. Inverted cone. So this is some sort of tank that looks like this. Um, Radius is 2. The height here is 4. And water is being pumped in at a rate of 2 meters per minute. So the water is going in like that, 2 meters per, or 2 meters cubed per minute. That's volume, right? dV dt is equal to 2. Okay, what's required? I want to know the rate at which the water level is rising. The rate at which the water level is rising. So at any point, the water is going to be sort of here, right? And there's going to be the height of the water. That's going to be h there, right? And then this is kind of going to be the radius of the water, r. You see that? And both of them are changing. The height's changing and the radius is changing because it's a cone shape. It doesn't have a constant radius like a cylinder shape. So this one's a little more challenging. I think we need to find dH dt, and it should be positive, when the water is 3 meters deep. So that's h is 3. What the radius is, well, we don't know. We might have to calculate it, but let's talk about the relationship then between right, we need a formula that relates these two. We actually have a little work to do in here as well in order to be able to do this. All right, well, what's the formula we're going to use? Volume of a cone. It's pi r squared h. That's the volume of a cylinder, then divided by 3. But notice, I don't have this constant r or constant h. Neither of these are constant. They're always changing. Both r and h are functions of t, right? And that kind of scares me. Notice I could just use the product rule here, but I don't know what dr dt is, right? I don't know what dr dt is, so I'm going to have to think about this. Well, it actually comes back to good old grade 10 similar triangles, right? Here I've got a relationship, right? 4 and 2, h and r. If I wanted to get a formula, because they're always going to be in this relationship, right? That's if I took a cross section of the cone, wherever it's going to be is going to be in this relationship. So it's going to be, you know, h to 4 is r to 2, similar triangles, and I can get a relationship between h and r. Now notice, I want to leave h in the formula, so I need to get rid of the r. So I'm going to multiply by 2 here, and I get r equals 2/4 h, or 1/2 h. And that's always true. And so I can use this formula and simplify this, so I do only have one variable in my equation. So I'm going to take out the r and put in 1/2 h. It's a bit of a mess, I realize that, but we can deal with it. I'm going to put the pi over 3 like this. Square the half is a quarter. H squared and h is going to be, the volume is actually pi over 12 h cubed. well, pi over 12h cubed. Now I can take the derivative. Now I can take the derivative, and somewhere in here was my solution. Maybe this is where I'm going to say my solution starts, because I'm ready to take the derivative. Take the derivative of the left side with respect to time. I have dv dt. Then the 3 comes down. H squared. Remember, h is changing with respect to t. So this is I was about to write h prime, but we have to be careful that we write. We know what variable we're taking the derivative with respect to, and it's time, like that. So what was dv dt? We should know all these things. dv dt is 2. I'm going to tidy this up right now. H, what was h? We had dv dt was 2. H was, we wanted to find dh dt when h is 3, when there's 3 meters in the tankette. All right. And then dh dt is what we're actually trying to solve for. Multiply by 4, divide by 9 pi. And there's my answer. Easy peasy. And that is about 0.28. Is increasing by 8 over 9 pi, which is 0.28-ish. And what is that? What are the units? Meters per minute. 0.28 meters per minute, 28 centimeters per minute, when it is 3 meters deep. Okay, that's it for the related rates problems. Have fun with your homework. It's actually the homework sections are in the appendix with the implicit differentiation stuff. They kind of put that stuff together for some reason, but we're covering it in our application. Certainly feels like an applications question, and we'll see some more application questions tomorrow.